Hi everyone, my name is Jia Yi I'm a PhD student from
Sorry, Wendy, there is a bit of background noise. Can you try now maybe?
Okay. My name is Jia Yi and I'm a PhD student from the University of Sheffield. I'm going to present the optical measurement of 3D surface fluctuations in partially filled pipe today. These photos shows significantly different surface patterns in low flow and high flow. Flowing water exhibits a unique surface pattern driven by the flow-induced turbulence. These patterns appears to be a function of underlying flow properties. Remote measurement of this pattern can therefore facilitate non-invasive assessment of the flow conditions. In today's presentation, I will show the experiment facility I used and the flow conditions I have examined, and introduce the optical technique I used for the surface measurements, DIC. And
sorry, Wendy, it's quite hard to understand. Can you maybe try and get closer to your microphone, or maybe use a different, I don't know if you have a headphone microphone headset.
Can you hear better now?
It's the sound, it's the noise rather than the video. Or maybe if it doesn't work, maybe we'll try to do with it. Maybe try to move farther away.
Is it better?
Not really.
Okay.
I'd say just try with this, and we apologize for the sound quality. If somebody finds it too disturbing, then maybe we can stop and find a solution. Okay. Go on, Wendy.
Okay. And some preliminary analysis from DIC. And I will talk about the advantages and disadvantages of this technique. All experiments are carried out in a 290 mils internal diameter and 220 meters long pipe. The measurement area is in the center sections of the pipe. The surface properties are measured from DIC, digital image correlation, wave probe, and microwave sensor. The underlying flow properties are measured by ADV, acoustic Doppler velocimetry. I will explain the details of this instrument in the later slides. 14 uniform flow conditions with different depths and flow rates were examined. The measured flow conditions were validated against series. The left figure shows the Manning's equations, and the right figures shows the dimensionless equations that shows the validation of the uniform flow conditions. Conductive wave probes give a linear calibration between their voltage outputs and water depths, so can be used to measure 1D surface fluctuations. In this experiment, a non-equidistant array of wave probes is used to collect surface data at multiple points to enable spatial analysis. Digital image correlation is an optical measurement method that has been used for displacement measurements in wide fields of applications. Wave probes gives instantaneous 1D surface shape measurements, while this DIC showing here is able to measure surface shape in 3D. To measure the instantaneous surface shape in 3D, water is colored white with titanium dioxide. A random pattern is projected onto the surface, and camera images the pattern from 2 directions to enable 3D reconstruction. Preliminary tests were carried out in a water tank. A wave probe is also placed inside of the water tank for reference. One time frame of the images taken by 2 cameras are showing on the top figure here. The 3D surface fluctuations can be recovered like the video showing here. The the blank area on the top right is where the wave probe is placed, and a gauge point near this area was selected. The wave probe voltage fluctuations and the evaluated water surface fluctuations at this gauge point from DIC shows comparable in both amplitude and frequency. As I have colored the water with titanium dioxide, it is important to understand how the addition of titanium dioxide will affect the surface dynamics of water. I have measured the same gravity waves fluctuations with different concentrations of titanium dioxide in. As you can see from the video here, the gravity wave is propagating and fluctuates up and down. 8 gauge points at different positions were selected, and the surface properties at these points were analyzed. We have published the findings on these experiments. It can be summarized that the titanium dioxide concentration above 0.01% substantially affect the fluid properties. About 1% is more significantly affected in gravity wave height and phase speed. Therefore, we recommended to use the lower concentration to more closely represent pure water dynamics. In addition, titanium dioxide must remain well mixed, so this technique is not recommended for low Reynolds flow or still water. To improve the clarity of images without adding too much of titanium dioxide, I added some liquid black dye into the water. This table shows the images taken on water with different concentrations of titanium dioxide and black dye. The addition of black dye improves the contrast and clarity of the pattern, resulting in more accurate data. A compromise must be found that gives good data while negligibly affecting the surface dynamics. For all of my experiments, I have used the 0.01% of titanium dioxide and 0.0055% of black dye. I hope you can see the moving surface fluctuations in this video showing here. These are the surface fluctuations recovered from the DIC for different flows. It is evidently to see the different roughness for different flows. With the increasing of the flow, you can see the higher roughness of the surface. Here, this figure shows the normalized histogram of the free surface fluctuations, and the lines shows the standard normal distribution, the Gaussian distribution for the water surface elevation. You can see the comparable results from DIC and wave probe data, and they show the similar trend that with the increasing of the flow rate, the standard deviation increased. This slide shows the power spectrums from these two devices. And DIC and wave probes show similar trends in high frequency range. And they show and you can see the decay of the slope shows a similar trend. With the accuracy measurement of the surface fluctuations, what we can get from this surface data, first thing is we can calculate the vertical velocity distribution by taking the time derivative of the surface fluctuations. And we can calculate the spatial and temporal cross-correlation by taking the cross-correlation at different points in the measurement area. And from that, we can get the surface velocity and can be compared with my ADV data showing on the left. And the figure on the right is the space-time matrix from the DIC measurement. You can see very clear and persistent features. The gradient of these striations indicates the advection velocity. And also we can calculate the frequency wave number spectra from in both streamwise and lateral directions from the DIC data. The DIC measurement is a low-cost, high-precision seedless technique that is not affected by the high turbulence intensity. The main limitations of this method are that the streamwise particle velocity cannot be obtained, and that areas of reflections and air bubbles in the images can result in noisy or missing data. And further study is required to assess the applicability in a field environment. In conclusion, the DIC technique is a seedless and non-contact way for accurate surface measurement. The surface measurement from DIC show comparable results with waveform measurement. With the accurate surface measurements, DIC is promising to extract the surface velocity. And there are still some challenges in the post-processing the images with air bubbles and reflections. That's the end of my presentation. Thank you so much.
Thank you, Wendy. Sorry again for the bad sound quality. So are there any questions for Wendy?
Sure. Todd Cowan here. I'll jump in. Wendy, that was fantastic to see. We've tried to do things like you're doing, and we have not had the success you have had. I'm wondering what the vertical resolution, the smallest sort of vertical measurement you have confidence that you think you can accurately measure is. Do you have a sense of that?
Yes, you mean the accuracy of the vertical measurement?
Yeah.
For my slowest waves, my smallest flow rate, the water fluctuations is within millimeters.
And do you think you're getting accuracies down then in the fractions to say 100 micron range, or is your accuracy uncertainty around a millimeter, which would maybe be where a traditional capillary or resistance wave gauge, a capacitance or resistance wave gauge would be?
I think the accuracy is within half millimeters.
Half millimeter. So you're still in the same order as traditional wave gauges, but now you can do it spatially.
Yeah.
Great. Thanks.
Any other question? I think there's time for another question, maybe for Wendy. Or if not, I will ask. So Wendy, you had to add some titanium dioxide because your water is very clear. So if you were to apply this in a more real life scenario, maybe with some turbidity in the water, or do you think you would be able to take measurements even without adding dye?
If the water is not transparent, this method can be worked.
Okay, so there are possibilities to take this to the field as well.
Yes.
Directly. Yes. Thank you.